to our professor, Dr. in Engineer Edgardo Uvas. A pleasant morning, sir, and welcome to my video presentations in compliance for the assessment number 2 in integral calculus. My name is Gilbert F. Sagaral, BSN for Mathematics student. Today, I am going to discuss volume of solids of revolution under the topic geometrical application of integration. Aside from finding the area of a function between curves, we can also use integration in solving for volume of figures. In finding the volume of a solid of revolution, we can use these three methods, namely the disk method, washers method, and cylindrical shell method, depending on the given situation. In this video, I will only solve some problems involving disk and washer methods to find the volume of the solid generated by a revolution. Geometrical application of integration, volume of solids of revolution. Let S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in the plane P of x through x and perpendicular to the x-axis is A of x, then the volume of a solid revolution is equal to the integration of A of x dx from A to B. Computing for the volume of a solid figure by integration, we will use first the disk method. For example, find the volume of the solid obtained by rotating about the x-axis the region under the curve y is equal to the square root of x from 0 to 1. Our solution, first we will graph the given function, which is y equals the square root of x from 0 to 1 and about x-axis. It will look like this in the graph. By graphing the function, we can form a certain shape that is circle. We know that the radius of a circle in this graph, we can find the radius of a circle from radius equal top minus bottom, which is the square root of x minus 0, because this graph is the function y equals the square root of x. Therefore, the square root of x minus 0 is equal to the square root of x. In finding the area of a circle, area is equal to pi times r squared, or the square of a radius. Then the volume will become the integration of A of x dx from A to B, where A of x is the area of a circle. Then the integration will become pi r squared dx from A to B, which is the integration of pi times the square root of x raised to 2 dx from 0 to 1 equals pi times the integration of x, because the square root of x when you squared will become x dx from 0 to 1. When you integrate x, will become x squared over 2 times 5 from 0 to 1. When we evaluate this, we get 1/2 pi cubic unit because we talk about volume. For us to adequately understand what we are talking about volume, let's say for example, this is the solid figure and we take the slice here, then we get the volume by adding those slices. Another example here, find the volume of the solid generated by rotating the region bounded by y equals x cubed, y equals 8, and y equals 0 about the y-axis. It is more like example number 1, but since it is y equals x cubed and about the y-axis. When we graph the function y equals x cubed, it will look like this. Since about y-axis, we will solve for the function in terms of y. When we substitute, when we interchange the variable, it will become x equals the cube root of y. In finding the radius, since this is the radius, when you form a circle here, will become right minus left, which is from the function the cube root of y minus 0. That's why our radius is the cube root of y. Then the volume will become the integration of pi times the cube root of y raised to 2 dy from 0 to 8. It will look like this. We will put the pi outside the integration or before the integration. that is equal to pi times the integration of y raised to 2/3, because the cube root of y raised to 2 is y raised to 2/3 dy from 0 to 8 is equal to pi times y raised to 5/3 all over 5/3, because the integration of this one will become this from 0 to 8. It will become 3/5 pi y raised to 5/3 from 0 to 8. When we evaluate this, it will become 96 over 5 times pi, or approximately equal to 60 and 319 thousandths cubic unit.